The following is based on a true story. All alterations have been made to make me look much, much cooler. This video goes over concepts of probability, and it also relies on a knowledge of logarithms. You should still be able to enjoy the video even if these are things you aren't familiar with. There it is. The Sphere of Destiny. I have no idea what it does, but with a name like that, a red crystal ball has got to be valuable, right? Alright, so what kinds of traps and barriers do we have this time? Puzzle locks? Hordes of ravenous enemies? A complicated tiled room where a single misstep will cause me to fall into a pit of spikes? Oh. A locked door with a password. Well, so much for an interesting adventure. Let me see here. Ugh, a full keyboard? You've got to be kidding me. The password could be anything, and it would take forever for me to calculate what it has to be. Unless... this should be able to do the job faster than I could. It costs a lot of chocolate coins, but I'm sure it'll be worth it.
Greetings, human.
Thanks for releasing me. What exactly are you? I'm a who, thank you very much. Name's Al. Al. Yup, I'm a demon who's really good at doing repetitive tasks quickly. I have a rhythm to it. A rhythm? Yup, it's how I go. It's a go rhythm. That might be the dumbest pun I've ever heard in my life. Hey, I didn't come up with it. I'm just following the script. Whatever. Look, there's a door that's locked by a password. Can you figure out how to open it? Well, without any clues, the only option would be to brute force it. I'll just have to guess a bunch of different passwords until I manage to land on the right one. Uh-huh. And how quickly are you supposed to be able to type them in? On a bad day, roughly around 400 billion a second. You're kidding. You'd be amazed how quickly these claws type. So, can I get started? Don't you have to figure out a strategy for how you're going to guess the passwords? I mean, I was just gonna start trying random stuff. It can't take that long to guess when I can type so quickly, right? I'm not so sure about that. I get the feeling there are a lot of passwords that it could be. I should probably figure out a plan for what the best method of cracking the password would be, and roughly how long it'll take to get the door open. If I just take this problem, and throw math at it, who are you talking to? I'll get my hands on that orb in record time. So, can I start now? Not until I figured out the optimum strategy. Were you even listening? Fine, I guess I'll just hang out over here then. Alright. With all those keys on the keyboard, there are a lot of different passwords to try. It's a bit overwhelming to imagine them all. If I were just to pick a random string of characters, it's hard to tell right now exactly how long it would take the algorithm to guess enough passwords in order to crack it. Obviously, if we're just guessing passwords over and over again, then randomness becomes something we need to worry about. But the thing about randomness is that, well, it's random. It'll be difficult to predict just how this is going to go. For instance, it's possible that Al could guess this string immediately, and so it would be cracked right away. On the other hand, it could be that they'll try every single password possible and pick this one last, which would mean I'd have to wait through every single other possible password, which could take a while. Are you talking about me? Let's try to make this much, much simpler. As simple as I can possibly imagine it. Well, the quintessential example of randomness is flipping a coin, so why don't we start with that? Let's say that there's a really simple password system where the password could either be heads or tails. Maybe I'll abbreviate those as H and T, respectively. Well, then the password can be one of two things. Either it's H or it's T. If I didn't know what the password was and I imagined flipping a coin to decide which password to guess, I'd have a 50% chance of guessing it right the first time. Of course, then I'd have a 100% chance of guessing it the second time, since there are only 2 passwords total. In just 2 guesses, I've exhausted all possibilities. pretty easy to crack, frankly. Okay, what if we make it so that a password is represented by multiple coin flips in a row? A sequence of flips. That would be more like what an actual password machine would have. Say a password made up of 5 characters. So if H represents heads and T represents tails, then something like HTHTT would be a valid password for this system. Just like before, I'll imagine guessing the password by flipping a coin 5 times in a row. Well, I guess at this point it makes sense to just come up with strings and try them out rather than actually flipping a coin. That'll be faster, and I won't have to worry about accidentally trying the same password twice. I know that each character has 2 possible values, H or T, and there are 5 characters in total. Each character has 2 possible choices, so the number of possible passwords is 2 times 2 times 2 times 2 times 2, or 32. Wait a second. There's a kind of doubling in difficulty going on here. A password of length 1 takes at most 2 guesses. A password of length 2 has 2 times 2 or 4 possible options, so that's the max number of guesses we'll need to make. A password of length 3 has 2 times 2 times 2 or 8 possible options. Since there are 2 choices, H and T, for each space in the password, the number of possible passwords doubles each time I add a character. In fact, it's really easy to calculate the number of guesses necessary. A length 5 password would have 2 to the 5th, or 32 possibilities. A length 10 password would have 2 to the 10th, or 1024 possibilities. So let's create a structure to work with. It can really be whatever I want it to be, but I think I'm going to use this doubling fact to help keep track of things. Let's say that the difficulty of a password to guess is the number of doublings that I need to run through in order to have tried every single option. A password of length 1 has 2 to the 1 choices, so I'll say that it's a degree 1 difficulty. A password of length 3 has 2 to the 3rd choices, so let's call that degree 3 difficulty. This is easy to scale up. If we have a password of length 20, then it would have degree 20 difficulty, because I'd have to guess 2 to the power of 20 passwords to make absolutely sure that I had the right one. 2 to the power of 20 is a little larger than a million different things I need to try. Obviously, on my own, that would take a long time, but given that Al can guess 400 billion passwords a second, it would only take him a fraction of a second to crack a degree 20 password. That's right, I'm amazing. Thank you. Note, it's perfectly reasonable to ask at this point why this is the structure I chose to measure difficulty. After all, if something takes a million guesses to exhaust every possibility, why don't I call it degree 1 million difficulty? Why bother with the power of 2 instead? There are a couple of reasons for this. First, the numbers here get really big really quickly, and humans aren't good at understanding the difference between large numbers. So it's more effective to use exponents to make the scale easier to read and understand. The second reason is that the actual mathematics behind these concepts is based around strings of bits that a computer would use. A bit can either be a 0 or a 1, so if we pretend that 0 is a heads and 1 is a tails, the structure matches. I want to make sure that people watching this video can do more research into the topic of password entropy if they want to, so I'm setting up a system that is directly analogous to its real-life counterpart. All that being said, you'll still be able to enjoy the rest of the video, even if this structure seems weird to you. I'll be using both the number of possible passwords and the difficulty level I described above when discussing password strength. Alright, let's set this difficulty structure to the side for a bit and try something more complicated. Can I finally start now? I could be in the quadrillions of guesses by now if you just let me start, you know. Patience, I'm not going to get started until I have the optimum strategy. Jeez, fine. Let's get to the keyboard now. There are still a lot of options, so let's try something simple first. Say the password can be made up of the digits from 0 to 9. There are 10 of those, so each character in the password has 10 possible choices. A nice round number. If we go with a 5-character password again, that means that there are 10 times 10 times 10 times 10 times 10, or 10 to the 5th possible passwords. That's 100,000 possibilities that I need to cycle through. Not really much of a problem given how quickly we can guess passwords. How exactly could I make the password more difficult to crack? After all, if it were my orb of destiny, I wouldn't want some 2-bit mathematician coming by to steal my goods. Well, obviously the keyboard has a lot of different characters besides the digits from 0 to 9 to choose from. If I allowed myself to use more characters, then each spot in the password would have more options. If I allowed the letter A as well, there would be 11 possible characters. And so the number of possible passwords would be 11 times 11 times 11 times 11 times 11, 11 to the fifth, or 161,501. What else could I do to make it harder to crack? Well, the only other way to change the password that I can think of would be to change the length of the password, either by having more than 5 or fewer than 5 characters in my string. If I can pick between 11 characters and I make the password length 6 instead of 5, then the number of possible passwords would now be 11 times 11 times 11 times 11 times 11 times 11, 11 to the power of 6, or 1,771,561. So, obviously, increasing the list of possible characters increases the difficulty, and increasing the length of the password also increases the difficulty. To make sure that I don't lose track of this, let's give things some names. I'll say the letter N stands for the number of characters that I'm allowed to use, and I'll let the letter L stand for the length of the password. A password that's length L and can choose from N characters will have a total number of possibilities of N to the power of L. This is just like what we said before. Picking between 10 characters with a length 5 had a total number of possible passwords that was 10 to the power of 5. How can I relate this back to the structure I designed with the heads and tails model? After all, if I have N and L, I need a way to express the difficulty in the same terms as the previous model. Otherwise, I just have a bunch of different models with no way to relate between them, and I'll have a hard time really thinking about the math that relates all this together. Well, earlier I said that a difficulty 20 password required a total of 2 to the power of 20 guesses to crack. Extending that idea, if a password is difficulty D, then it'll take 2 to the power of D guesses to crack it. There's an equation buried in here somewhere. Let's say that a password with N characters and of length L is a difficulty of D. On the one hand, I'll need to guess N to the power of L times to get every password. On the other hand, since the difficulty is D, then according to my definition, I'll need to guess 2 to the power of D times to get every password. That means these two things are actually the same, since they both represent the number of possible passwords. We get the equation N to the power of L is equal to 2 to the power of D. Okay, the letters here are starting to make me confused, so let's go to a specific example. Earlier I said that if I can choose from digits 0 to 9 and the letter A, and my password is 6 characters long, then the number of possible passwords is 11 to the power of 6, or 1,771,561. Pretending that I know what the difficulty level D of this password is, it must be the case that 2 to the power of D is equal to 1,771,561. So, what is D equal to? What is the difficulty level of this password? To solve an equation like that, I need to find a way to undo the 2 to the power of D and solve for the variable. Seems tricky though. I can't add, subtract, multiply, or divide by anything to get the D by itself. What to do? Oh wait, I might have something here in my bag. There we go. The best method for this problem will be to use a logarithm of base 2. That's what the logarithm is, after all. It tells you what the exponent is in an equation like this. The log base 2 of 32 is 5, since 2 to the power of 5 is 32. The log base 2 of 1024 is 10, since 2 to the power of 10 is 1024. So if 2 to the power of D equals 1,771,561, then using the same pattern, D is the log base 2 of 1,771,561. Unfortunately, figuring out D here is pretty difficult because 1,771,561 isn't actually a power of 2. 2 to the power of 20 is this, and 2 to the power of 21 is this. 11 to the power of 6 is between those two. So the difficulty D must be somewhere between difficulty 20 and difficulty 21, some decimal amount. Luckily, a calculator can use a logarithm function to figure out what that fraction ought to be. I have that function too, by the way. Just saying. Do you now? Yup, it's another thing I have a rhythm for. Oh no. It's a system I use with cutting down trees. Don't you dare. It's a logarithm. God damn! Okay, so according to my calculator, log base 2 of 1,771,561 is about 20.76. So a password with 11 characters to choose between and a length of 6 has a difficulty level of 20.76. I think I'm getting the hang of this. If I go back to the letters, then I have the equation 2 to the power of d is equal to n to the power of l. To get d by itself, I'll use the log base 2, just like I did before. So, d equals log base 2 of n to the power of l. Now I have a handy little equation that will tell me the difficulty of any password, as long as I know what n and l are. Actually, there's a special log rule I can use here to make this even nicer. It turns out that I can just pull this l down in front, and the equation will still be exactly the same. Logarithms are weird. So, our final result is that the password of length L, picked from n characters, will have a difficulty level of L times log base 2 of n. Not bad. Okay, are you finally finished? This is taking forever. I'm getting there, okay? Just give me a minute. I've already given you several. I'm getting bored over here. Be patient. I think I'm about to crack this wide open. Sure you are. Al says that they can guess 400 billion passwords a second, which seems like a ton, but how does that compare in terms of the difficulty level I've created? What difficulty level would be high enough that even they can't crack? Well, how long am I willing to sit here before it's no longer worth it? I could probably last a day before losing my mind. Maybe. Okay, so 400 billion passwords a second is 24,000 billion guesses a minute, which is 1,440,000 billion guesses an hour, and 34,560,000 billion guesses a day. Or to put it in clearer terms, 34 quintillion 560 quadrillion guesses a day. Good lord. If a password takes that many guesses to crack, what's its difficulty level? Well, we just need to take the log base 2 of that monster, which gives us roughly 54.94. Okay, that'll be my line in the sand. If the password to the Orb of Destiny has a difficulty level bigger than 54.94, then I'm going to give up on this one. Let's mess around a little more with this equation. Going back to my simplest example, let's say I have the digits from 0 to 9, 10 characters in total, as well as a password of length 5. The difficulty of cracking this password is 5 times log base 2 of 10, or about 16.61. But most people would put both letters and numbers in their passwords. If we assume just lowercase letters right now, then there are 26 characters there, plus 10 characters for the numbers, which gives us 36 characters in total. A length 5 password with this character pool would have a difficulty of 5 times log base 2 of 36, or about 25.85. Piece of cake. I could wait around for that one. What if I did the digits from 0 to 9, but changed the length of the password to be 10 characters long? Well, then according to this equation, the difficulty would be 10 times log base 2 of 10, or about 33.22. Wait a second. In the first case, I increased the number of characters by 26. In the second case, I increased the length by 5. An increase of 26 characters seems like a much bigger change than an increase of length of 5. So why does the increased length password have a higher difficulty rating than the increased character password? Something's going on here. Oh, wait. I'm remembering something from my training. Logarithms are notorious for a lot of things, but one in particular is just how slowly they get bigger. If you look at a graph of a logarithm, you can see that even though it's always getting larger as you plug bigger and bigger numbers in, it's growing extremely slowly. In the formula I created, the n is trapped inside of a logarithm, while the L is not. I know that either increasing L or increasing n will make the difficulty larger, but the log around the n means that I have to increase n a huge amount to see much of a difference, since the logarithm grows so slowly. On the other hand, L isn't restricted like that and can grow at a much faster rate. Strange. So I guess that means that increasing the length of a password makes it far more difficult to crack than increasing the number of characters that you can use. I'll have to remember that next time I need to set a password up. Okay, time to actually solve this problem. The password on the door lock has a total of 16 slots, which means that the password can be a length of 16 characters. The password can be made up of numbers, lowercase letters, uppercase letters, and these 10 symbols. So the total number of characters we can choose between is 72. So if the password creator took advantage of all of these things, then the difficulty level of cracking this password would be 16 times the log base 2 of 72, which is about 98.72. Uh-oh. My threshold for wait time was 54.94. That's way beyond how long I'm willing to wait. In fact, if I calculate how long it will take Al to guess 2 to the power of 98.72 passwords, it would take around 40 million millennia. I definitely don't have that kind of time. But maybe I can make my plan better. After all, who makes their password a random string of characters? There could be other patterns here that I haven't explored yet. What if the password is made of common English words? Then I could try guessing the words instead of the original letters, and that would make it much faster to... What? Can't you see I'm calculating here? You're welcome! Ungrateful little punk. Thanks for watching. The topic of password entropy has a lot of angles that I didn't explore in this video, and there are a lot of ways that computer algorithms can try and get around the limitations I presented here. I've linked some excellent videos in the description that talk about how to create the safest passwords, so I hope that you'll watch them and commit to keeping your data safe. See you in the next one.